Even though we have developed our cosmological model based on observations, theories, and the mathematics supporting those theories, there are a few signs that the universe isn't entirely consistent. You might have heard about the crisis in cosmology. Essentially, this crisis began when different methods of measuring the universe's age started yielding varying results, and this discrepancy continues. The James Webb Telescope, with its recent images, has exacerbated the crisis even further. We have a video discussing the crisis in cosmology, which you can view by clicking the link in the description. For now, here's a very brief refresher. The Hubble tension. The universe is expanding, and distant galaxies are moving away from us. When we calculate the rate of this expansion using the cosmic microwave background, the light remaining from when the universe was just 380,000 years old, this is what we find. There's another method where we know how bright distant supernovas should be, and we compare this to their observed brightness. This information helps us estimate the universe's expansion rate at the time of the supernova. The expansion rate, known as the Hubble constant, differs between these methods, creating what's called the Hubble tension. This is the heart of the cosmology crisis, but it's not the only issue. The S8 tension. A new crisis, a distant cousin of the cosmology crisis, has emerged. This new issue is particularly troublesome. A scientist noted, "I have spent my entire career developing a specific theory of the universe, and now that theory is being questioned. I welcome this because it's how we progress in science. When we look up at the sky, assuming you're not in a city with obstructed starlight, you see countless stars and the Andromeda galaxy as a smudge among them. This is because the universe is filled with stars and galaxies. The question now is, the S8 tension. How much of the universe is filled with these galaxies and stars? In other words, how much matter is actually present? The answer to this simple question is complex due to current cosmological observations disagreeing on how matter is distributed in today's universe, leading to the S8 tension. The S8 tension measures the lumpiness or clustering of matter in the universe. Imagine the universe as a vast puzzle where the pieces are matter scattered across space. Scientists aim to understand how this matter is distributed and how it clusters. There are two ways to measure this. 1. By calculating it using low redshift observations such as weak gravitational lensing. Gravitational lensing occurs when the immense gravitational pull of massive objects like black holes and galaxies acts as cosmic magnifying glasses, bending and distorting light from more distant objects that would otherwise be invisible. 2. The second method uses the standard model of cosmology based on cosmic microwave background measurements. However, the S8 value from this method does not align with values from low redshift observations. This discrepancy forms the crux of the S8 tension. The FLAMINGO project. To address the S8 tension and gain deeper insights, astronomers used one of the world's most powerful supercomputers for the largest ever cosmological simulations. The FLAMINGO project, a convoluted acronym for Full Hydra Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observations, required over 50 million hours of computer time across 30,000 processors of the Dr. Cosmo 8 supercomputer at Durham University in the UK. Unlike previous simulations focused solely on dark matter, FLAMINGO includes ordinary matter too, tracking its role and effects on cosmic matter distribution, such as galactic winds powered by supermassive black holes and supernova explosions. Despite its comprehensive approach, FLAMINGO failed to fully explain the observed weak clumping of matter in the present universe. This shortfall leaves unresolved the S8 tension and raises significant questions about our current understanding of cosmology. It suggests that our standard model may have deeper flaws or that unknown factors are influencing the universe's structure. The discrepancies highlighted by the FLAMINGO simulations extend beyond theoretical predictions to contradict observations made by advanced telescopes like the James Webb Space Telescope. These observations provide valuable insights into the distribution of matter, presenting a formidable challenge for cosmologists and astrophysicists. They force us to confront the limitations of our current models and rethink our understanding of the cosmos. The FLAMINGO simulations and the S8 tension they expose are not failures but rather opportunities for scientific progress. They push us to question our assumptions, explore new theories, and advance our knowledge of the universe. As we grapple with these challenges, we are reminded of the vastness and complexity of the universe and the continuous journey of discovery and refinement that drives science forward. The upcoming shift in cosmological understanding promises to be significant, underscoring how science evolves through persistent inquiry and adaptation. Historical background of cosmological models. Cosmology has a rich history, evolving from early astronomical observations to sophisticated theoretical frameworks. Ancient civilizations like the Babylonians and Greeks made initial attempts to understand the cosmos, with figures like Ptolemy proposing early models of the universe. The geocentric model dominated for centuries until the heliocentric model proposed by Copernicus in the 16th century marked a significant paradigm shift. This model was further supported by Galileo's telescopic observations and Kepler's laws of planetary motion. The 20th century brought revolutionary changes with the advent of the Big Bang theory. Edwin Hubble's observation that galaxies are moving away from us led to the formulation of Hubble's law and the understanding of an expanding universe. This was a crucial development in cosmology, aligning with the general theory of relativity proposed by Albert Einstein. The discovery of cosmic microwave background radiation by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang model, establishing it as the leading cosmological paradigm. Details of observational techniques and instruments. Observational cosmology relies on a range of sophisticated instruments and techniques. Ground-based telescopes, such as the Keck Observatory, offer high-resolution imaging and spectroscopic data, while space telescopes like the Hubble Space Telescope have provided unparalleled views of the universe by avoiding atmospheric interference. The James Webb Space Telescope, JWST, launched in December 2021, represents a significant advancement in observational technology. Equipped with infrared capabilities, JWST aims to peer further back in time than its predecessors, allowing scientists to observe the formation of the first galaxies and stars. Techniques such as gravitational lensing exploit the way massive objects bend light to study distant galaxies. Observations of the cosmic microwave background, CMB, radiation help in understanding the early universe's conditions. Other methods, including supernovae surveys and baryon acoustic oscillations, provide insights into the universe's expansion rate and the distribution of matter. Theoretical frameworks and their evolution. Theoretical cosmology has evolved from Newtonian mechanics to complex quantum field theories. The standard model of cosmology, known as lambda cold dark matter, lambda CDM, incorporates a cosmological constant, lambda, associated with dark energy and cold dark matter. This model explains many aspects of the observable universe, including the large-scale structure and the cosmic microwave background. Modifications and extensions of the standard model, such as theories involving warm dark matter or modifications to general relativity, are also considered. Theories like inflation, proposed by Alan Guth, address the uniformity and flatness problems of the universe by suggesting a rapid expansion during the early moments of the Big Bang. The intersection of cosmology with particle physics, particularly the study of dark matter and dark energy, represents a dynamic and evolving area of research. The quest for a unified theory of fundamental forces continues to drive theoretical advances. Detailed analysis of the Hubble tension. The Hubble tension refers to the discrepancy between the expansion rate of the universe measured using the cosmic microwave background, CMB, and the rate determined from local measurements of supernovae and Cepheid variables. The CMB, observed by missions like the Planck satellite, suggests a lower rate of expansion compared to measurements obtained through local observations. The implications of the Hubble tension are profound, challenging our understanding of fundamental cosmological parameters. Possible explanations include errors in measurement techniques, the need for new physics beyond the standard model, or a reassessment of the assumptions underlying current cosmological models. Studies continue to refine measurement techniques and explore theoretical models to address this tension. In-depth look at the S8 tension. The S8 tension concerns the distribution and clustering of matter in the universe. The parameter S8 combines measurements of the universe's matter density and its clustering amplitude. Observations from the CMB and large-scale structure surveys provide different values for S8, leading to a discrepancy. This tension has significant implications for our understanding of dark matter and the processes governing matter distribution. Detailed analyses involve studying galaxy surveys, weak lensing, and simulations to reconcile these differences. The FLAMINGO project, among other initiatives, aims to address this tension by incorporating various factors into simulations. The role of supercomputers in modern cosmology. Supercomputers play a crucial role in modern cosmological research, enabling simulations that model complex processes across vast scales. The FLAMINGO project, using the Dr. Cosmo 8 supercomputer, represents a monumental effort to simulate the universe's evolution with unprecedented detail. Supercomputers allow researchers to explore scenarios that are otherwise infeasible, such as the detailed impact of ordinary matter on cosmic structures. They enable the integration of various factors, including dark matter, baryonic matter, and feedback processes, into simulations. The results from these simulations provide insights into the discrepancies observed in cosmological models. Comparative analysis of cosmological simulations. Comparative analysis of different simulations helps in understanding their strengths and limitations. Simulations like those from the FLAMINGO project are compared with observational data to test their accuracy. Discrepancies between simulations and observations highlight areas where our understanding of the universe may be incomplete. The use of diverse simulations helps to identify common trends and differences, providing a more comprehensive view of cosmic evolution. This process is iterative, with each simulation contributing to a refined understanding of the universe's structure and dynamics. Implications of discrepancies for future research. Discrepancies in cosmological models drive future research by highlighting gaps in our understanding. They prompt scientists to question established theories, explore new models, and refine observational techniques. Addressing these discrepancies involves interdisciplinary collaboration, combining insights from astronomy, physics, and computational science. Future research may involve new observational techniques, advanced simulations, and theoretical models that incorporate recent findings. The goal is to achieve a more accurate and unified understanding of the universe's structure, evolution, and fundamental properties. Case studies and key discoveries. Case studies of key discoveries in cosmology illustrate the progression of our understanding. Examples include the discovery of cosmic microwave background radiation, the identification of dark matter, and the observation of the accelerating expansion of the universe. Each discovery has contributed to shaping current cosmological models and addressing outstanding questions. Examining these case studies provides context for current research and highlights the iterative nature of scientific progress. They demonstrate how new discoveries build on previous knowledge and drive the evolution of cosmological theories. Philosophical and conceptual implications. The philosophical and conceptual implications of cosmological research extend beyond empirical findings. Questions about the nature of the universe, the role of fundamental constants, and the origins of cosmic structures challenge our understanding of reality. Debates about the nature of dark matter, dark energy, and the limits of human knowledge reflect broader philosophical inquiries. These discussions shape our interpretation of cosmological data and influence the direction of future research. Conclusion. The journey through the complexities of cosmology reveals both the progress made and the challenges that remain. As we advance our understanding through observations, simulations, and theoretical models, we confront fundamental questions about the universe. The ongoing quest to reconcile discrepancies and refine our models underscores the dynamic nature of scientific exploration. The FLAMINGO project and other initiatives exemplify the effort to address these challenges, pushing the boundaries of our knowledge. The discrepancies uncovered highlight the need for continued inquiry and adaptation in cosmology. Through persistence and innovation, scientists strive to unlock the universe's secrets and gain deeper insights into its nature and our place within it.